So do we have enough people back from the break to get started? Yes? All right. So welcome to the session on Asian dust, which has become a little bit shorter as there are only 2 talks. The first one is by Balint Alfoldy, which is optical absorption properties of mineral dust particles generated by storm events in a desert environment. And this,
No. Thank you. Good morning, everyone. So my name is Balint Alfoldy. I am basically from Hungary, but I am working in Slovenia at the aerosol company. This company is the manufacturer of the AE33 atalometers and other devices regarding carbon aerosol measurement and analysis. And maybe you are wondering what we are doing here in a dust conference with our carbon detection instruments. So shortly I will enlighten you. I am not going to emphasize the importance and climate effect of mineral dust because other speakers already did before me, even better than I could. So I immediately jump into the middle and tell you what we did, why we did, and how we did. So not only black carbon absorbs solar radiation and other light, but also mineral particles do with different extent depending on the mineral composition of the particles. So this would, let's say, offer an extension of the applicability of our devices, and atalometers could provide a unique measurement opportunity for real-time monitoring of mineral dust concentration with very good time resolution, means minutes. And first, to check the applicability of our instruments, it's better to move the place when mineral dust is really an issue. So that's why we moved to the Arabian desert in Qatar and tested our devices there. And especially we were happy that some dust storm happened during our study, because this offer well-defined conditions when the particle composition is dominated mostly mineral particles and the contribution of anthropogenic sources are minor. But there is still a problem because the absorption of mineral particles are still low, and especially comparing to black carbon. So if we have any black carbon around, it would interfere the measurement. So that's why we need a technical solution to avoid it, and this can be happen with the separation of coarse and fine particle fraction based on the aerodynamic diameter with the so-called virtual impactor technique, because we can, let's say, assume that the black carbon particles are mostly in the fine fraction, while the mineral dust in the coarse fraction. So how does it works? My colleague Matic already introduced this technique on Tuesday. Now I just briefly repeat it. So we have a major flow here with 100 liters per minute, And in the virtual impactor, this flow turns to perpendicular to the original flow. And of course, the mineral particles, which are big and has high inertia, they cannot follow this sudden change of the stream. So that's why they want to continue straight. And the minor flow with 2 liters per minute, we sampled straight, parallel to the initial flow, and this is analyzed by the AE33 attelometers. So thanks to this inertia of the big particles, the mineral particles are in this minor flow, and the extent of the concentration can be seen in this figure. So it's roughly 11 times concentrated. So after the measurement, we have to, let's say, correct back with this factor. So the setup is the next. We have this. We have to operate 2 attelometers. One with the VI inlet. This is here, which measuring the coarse particles, and we need another attelometers with PM1 inlet, what measure the absorption of the fine particles, which supposed to be black carbon. So if we have something remain in the VI sample, we can make a correction of the absorption of black carbon particles. So this equation shows how this correction works. So if we want to have the dust absorption, we have to subtract the absorption of PM1 fraction from the VI absorption and then divide by this enhancement factor, what was the concentration factor of the coarse particles. And after we have the absorption, yeah, this plot shows how the color of the tape changes after a Saharan dust episode. So the black dots convert to this whitish color due to the sampling mineral particles. So after we have the absorption of the dust particles, we can calculate the concentration of the mineral particles if we know this Mach value, the mass absorption cross-section of the mineral dust particles. So the location of the study, it was, as I told, in Qatar, let's say 50 kilometers north to the capital, but it's close to, and also it's downwind location from Ras Laffan region, what is a gas processing industry. So some impact can be, let's say, expected from here. And on the station, we were operated this VI PM1 attelometer system. And also we did PM10 filter sampling in every second day. So this 1 day, so 24 hours filter sampling to measuring the PM10 total mass. And this is the storm event, what I already mentioned. So first look at the atmospheric pressure. It's a really nice behavior. First look at this periodic changes. It's for me it was very nice to see. This was the first time I see this effect. It is the so-called atmospheric tide. So here in Europe and in the, let's say, middle latitude, we cannot see these changes, but close to the equatorial, it is more visible. So it's the same like the ocean tide, but regarding the atmosphere. So this periodicity is absolutely linked to the movement or the rotation of the Earth. But what is now more important is drastic drop of the pressure. What followed this a huge vortex here, and actually this was the time when the dust hit the measurement location. Also, we can see the changes in the temperature. It was gradually increasing, and then suddenly dropped, and everything changed after this moment. So in this figure, it looks quite dramatic view of the arrival of the dust frontier, and this was how the city looked like during the storm. So it was a really apocalyptic, let's say, vision of the event. And what we measured. So this is this figure shows the concentration measured by the VI station. This is the orange line, and the PM1 station. This is the blue line. And the storm started here. It is clearly shown these huge spikes, and I even cannot. The scale is smaller than it would needed, because the maximum concentration was 160,000 nanogram per cubic meter. But this is the, let's say, equivalent black carbon concentration. It's not the mineral concentration, because our instrument readings shows the black carbon. So it means that if this absorption would been caused by black carbon, this would be the concentration. But regarding mineral dust, since the mass absorption cross-section for mineral dust is much lower than black carbon, it means that regarding mineral dust, this concentration is even higher. Later, I will show you what was the concentration. If we zoom in to the scale and show the PM1 and the VI concentration in separate scale, we can see some, let's say, related or anticorrelated behavior of the two concentrations. So when the storm starts, it's interesting that on the coarse fraction we have this huge peak, while in the fine fraction it's nothing happened. But in the fine fraction, the peak came later, when in the coarse fraction is already gone. So what does it mean? Does these two components affected by mineral dust, or something happened with the black carbon also? And what about the other peaks? So here we can see some peaks when the VI and the PM1 are correlated, here, and here. But other peaks, only we see peaks in the PM1 fraction, here and here, or only in the VI fraction, or the coarse fraction, here and here. So what does it mean? It means that it's a different kind of particles, or what is happening. So for this, we have the ability to check the spectral, let's say, behavior of the sample, because our instruments measuring the light absorption at 7 wavelengths. So it is able to study the spectral behavior of the particles. So from the Angstrom law of light absorption, it is known that the absolute black body, like black carbon, the absorption follows this kind of power law with the exponent of -1, and so this exponent called absorption atomic absorption Angstrom exponent, and for black carbon is around 1. And this is how it looked like in our instruments. So here are the 7 wavelengths from 960 to 370. And this is a nice, let's say, power law relationship. What about during this storm? So during the storm, this spectral dependence looked like this. So the blue line shows the the same like this. So absorption with angstrom exponent 1, and we can see that the measured data are much higher, has much higher absorption below 580 nanometers. So it means that the mineral particles has, let's say, higher absorption in the short wavelengths and in the UV domain. So it could offer us a good tool to distinguish the black carbon particles from the mineral particles, because black carbon has still, let's say, moderate absorption at short wavelengths comparing to the mineral dust, which has this huge absorption. So let's check what happened in the PM1 fraction. So this is this peak, and we see the same. So the measured absorption is much higher than it would expect from the black carbon. So it means that this peak can be linked to mineral dust particle, so not black carbon, as we expected. So we expected that in the fine fraction, black carbon should be and the minerals should be in the coarse. But it shows that during the storm, even the fine fraction was dominated by mineral particles. And in this second peak here, what was in the next day, shows the same behavior. So it means that thanks to that vortex, what I showed in the previous slides, this dust plume or dust cloud returned on the second day and caused this second peak here after this transition period. While other peaks, when the VI and the PM1 fraction are correlated, we see that the absorption follows this black carbon-like absorption. So these peaks are not related to mineral dust. Even we have huge peak in the coarse fraction, these particles are related to black carbon and not mineral dust particles. So since it looked that the difference in absorption happened below 600 nanometer, we should split the spectral range into two, let's say, interval. One is above 600 and the other one is below 600. So here in this figure shows the two angstrom exponents. So one is, the red is related to the long wavelengths, and the pink related to the short wavelengths. And it is seen that for the long wavelengths, the exponent is quite stable around 1 during the whole period, while the short wavelengths, we have these huge peaks when the PM1 fraction was also high. So it means that this short wavelength angstrom exponent is a very sensitive indicator for the composition of the sample to distinguish the mineral particles from black carbon. So yeah, these are the two events. Okay, so now we are at that point that we want to convert the absorption of mineral dust to the concentration. So for this, we need this mass absorption coefficient value. But we are in a lucky case because we have the PM10 measurement. So we have, let's say, the daily average of the corrected absorption of the coarse fraction, and we have the PM10 concentration, so we can calculate the Mach value from this equation. So the results are here. It is it shows some variation from 0.02 to 0.07, and let's compare it to other studies. So this is this study, and 0.04 was during the storm. So it's let's say it's the pure mineral case. But previous studies shows higher values. So, for example, my colleague on Tuesday, he reported 0.1, while we can find in the literature also 0.2, 0.1, 0.2. So compared to these numbers, our values much lower. So at the moment, we don't know what is the reason. It can be that maybe we overestimate the PM10, or there are other components in the PM10 that don't absorb the light. So it needs more investigations. So let's move to the conclusions and the limitations, or some possible future application of the results. So the light absorption of mineral dust was possible to be measured by the atalometer technique by high time resolution in the concentrated VI sample. And the light absorption was possible to measure even in the PM1 fraction during the storm event. And below 600 nanometer, the angstrom exponent was found to be a sensitive parameter to distinguish absorption of mineral particles from black carbon particles. But there is a problem because the brown carbon and the organic carbon has also enhanced absorption below 600 nanometer. So here in the desert, this technique could work because we don't expect too much brown carbon and biomass burning. But in other locations where there is important biomass burning, it could interfere this technique. The MAC value, what we found, was lower than in previous studies. And further studies should involve the mineralogical analysis of the dust sample in order to link the measured absorption to the mineral composition, because we expect that different composition of minerals could have different absorption. And just after this conference, I had the idea that maybe the volcanic dust would be a good subject also for our technique, because it's also dark, so absorb the light. And as there was a talk on Tuesday regarding this photoacoustic technique, and they showed the same behavior than during in the short wavelength interval. The absorption was much higher than black carbon, so maybe this technique would could be extended to studying volcanic dust. And that's all. Thank you for your attention.
Any questions from the live studio audience?
Thank you, Balint, for these interesting and detailed investigations. My simple question is, can a mineral dust species is it able to masquerade as a black carbon by absorption? Because these concentrations of mineral dust particles are so high that gathering or absorption of black carbon particles is thinkable. It's envisaged. And so the question is there a combination that the black carbon particle actually is much larger and still gets through into the minor flow?
Yes, definitely the black carbon particles, we can find the black carbon particles in the minor flow because, actually in the same concentration, which is in the ambient case. So that's why we need the other atalometer, the second one, with the PM1 inlet, which is measuring only the black carbon. We don't expect coarse particles or mineral particles in this size range. So that's why we're measuring the black carbon in PM1 fraction and then subtract from the absorption of the VI. It was not the case during the storm, because during the storm, even in the fine fraction, we found the mineral particles. But usually, when it's normal case, not storm case, it can be supposed that in PM1, the black carbon dominates the absorption. So that's why with the other instrument, we subtract the absorption and get the pure mineral absorption in the coarse fraction.
Anybody else? I see one comment in the chat. Do we have any online questions? No? Okay. Well, thank you.
Thank you.
And my understanding is that rather than wait till 12, we are going to do the next talk right now, which is a recorded talk. And that is by Arya V B, Possible Indirect Effect of Dust Aerosols During Monsoon Breaks Over India.
Good morning to all. I am Arya V B, ACSAS student from India. Today, I am going to discuss about possible indirect effect of dust aerosols during monsoon breaks over India. We know that aerosols are the tiny suspended solid or liquid particles present in the atmosphere. These particles play a vital role in the Earth's climate system. Aerosols can have direct impact through absorption and scattering of the solar radiation. This aerosol particle can act as cloud condensation nuclei or ice nuclei for the formation of clouds. Aerosol particles modify the cloud property, which is known as the indirect effect. Coming to the Indian summer monsoon. We know that Indian summer monsoon is the world's strongest monsoon system, which provides 80% of India's annual rainfall. Indian summer monsoon and associated rainfall exhibit a wide range of variation over spatial and temporal scales. Summer monsoon rainfall involves interaction between land, ocean, and atmosphere, and it also depends on many processes, including remote factors. Apart from the large-scale forcing, anomalously and markedly different onset and sub-seasonal progression of summer monsoon in a particular season can occur by the virtue of the internal variability of the Indian summer monsoon system. For a monsoon system, the intra-seasonal variability, such as mainly two variability ranges from 10 to 20 days, which is known as quasi-biweekly, and 30 to 20 days monsoon intra-seasonal oscillation. The dominant more low-frequency component of intra-seasonal variability, that is 30 to 60 days time scale monsoon intra-seasonal oscillation, are characterized by the northward propagation of cloudiness and the precipitation over Indian region. And this mode basically determines whether drier than the normal is known as active or break spells of rainfall during the monsoon season, which is found to be the dominant factor in deciding seasonal monsoon rainfall. Summer manifests as break, that means with below normal rainfall, and active with good rainfall over Indian region, especially over the monsoon subzone. This figure shows the daily variation of rainfall over the monsoon zone for the year 2002 and 2007. Here we can observe that for the year 2002, there is a long and intense prolonged breaks are observed. Whereas in 2007, we can observe this strong active spells. Comparing these 2 years, there is evident distinct difference in numbers, duration, and intensity of the break and active spells. We know Indian subcontinent with various geographic features, dense population, and with different industrial zones is a source region for different types of aerosols. Numerous studies have shown that absorbing aerosols like dust and carbonaceous aerosols can affect the intra-seasonal variability and the inter-annual variability of the Indian summer monsoon rainfall. The study by Hasra et al. Shows an increase in absorbing aerosols during the break phase results in a larger landscape temperature disparity and intensified moisture transit, which leads to an active stress. Using recently available measurements of aerosol and cloud property available since last 15 years, we address the evidence supporting the role regional aerosol might play in monsoon active break spells. Next, moving to the active break composite aerosol characteristics. This figure shows the composite anomalies of AOD and rainfall. Top panel shows AOD and the bottom panel shows rainfall. For the rainfall, for the active phase, we can observe that there is an increase in rainfall amount over the CTC region and the West Coast. Whereas a decrease in rainfall is observed over the foothills of Himalaya and northeastern region. And in contrast, for the break phase, the rainfall shows increased rainfall. For the break phase, there is decreased rainfall observed over the CTC region and West Coast, whereas increase in rainfall is observed over the foothills of Himalaya and the northeastern region. Coming to the aerosol optical depth, during active phase, the active composite of AOD shows there is a decrease in aerosol loading over India during the active phase. And in the break phase, there is the enhancement in the aerosol loading over Indian region. Next, we analyze the composite anomalies of wind and the divergence. The active phase is characterized by cyclonic circulation with associated large-scale convergence of wind over central India. There is anomalous anticyclonic circulation during the break phases observed. The strong westerly winds during the break phase transfer huge amount of aerosol from the western part, especially from the West Asia, Thar Desert, African region. That is mainly the dust aerosol from the desert region. Next, we check the contribution of dust aerosol to the total AOD using Calypso data. Here, the figure shows the percentage of dust AOD with respect to the total AOD over grids from the Calypso track for active and break composites. It is clearly shown that break period is associated with significant dust loading over Indian region, with dust AOD hugely contributing to the total aerosol optical depth. Next, we examine the variation in vertical profile of latent heat and moisture sink. The composite vertical profile of latent heat and the moisture sink derived from the daily data average over the CTC region for the active phase, that is the dashed line, and for the break phase, that is solid. We can observe that both quantities show distinct difference for active and break phase. We will observe that for break phase, both quantity is minimum, that is, it is very less. We can observe. So, we observe that for the active and break phase, there is a distinct difference in aerosol loading. Then, we analyzed the variations in cloud, the anomalies of the composite anomalies of cloud properties during active and break phases. This figure shows, the first panel shows the cloud optical thickness, composite of cloud optical thickness during active and break phase. We can observe that for the active phase, there is an increase in COT for the CTC region and West Coast of India, but it is decreased in the foothills of Himalaya and northeastern region. And here, for the opposite is observed over the Indian for the break composite. Then coming to the cloud effective radius, that is for the break phase, that is for the break phase, increased amount of aerosol cause decreasing amount of decrease in the cloud effective radius. So we can observe the cloud effective radius is decreased over the western part, whereas it is increased over the western part for the active phase. But there is a slight disagreement for the eastern part of the India, and this is due to heterogeneous ice nucleation. Then coming to the cloud water part, cloud water part also shows distinct difference for the active and break phases. Overall, the anomalies in cloud properties such as cloud effective radius during break phase when AOD is anomalously high over India suggests the possible indirect impact of aerosols. Next, we analyzed the average anomalies of AOD and rainfall over the CTC region. The figure shows the mean AOD and rainfall anomalies average over the CTC region for three categories. That means for the break we categorize as 3 to 5 days AOD and rainfall anomalies, then 6 to 8 days and greater than 9 days. And for the active phase is classified as 3 days, 4 to 5 days and 9 days. Here, you can observe that AOD anomaly increases systematically with increase in the duration of break spelling. The clear association of AOD and rainfall anomalies are not observed for the active spells. But for long break, the increase in aerosol content can reinforce and extend the breaks. Then coming next, we analyze the flex, variation in the flexes, that is top of the atmosphere short wave flex and top of the atmosphere long wave flex. So this composite anomaly for short wave flex shows that for the active phase it is positive, whereas break phase it is negative. That is, this hints during break phase the impact of the semi-direct aerosol does induce semi-direct impact. Next, we analyzed that the vertical temperature anomaly, that is composite of vertical temperature anomaly over the Indian region for 6 break days composite and 30 break day composite. Here we can observe heating in the atmosphere is caused by the absorption of solar radiation by aerosol. Greater the quantity of absorbing aerosol, greater the atmospheric heating. But it is that for this analysis, it is observed that for the longer break days, the heating is more intense than the shorter break days. Next, we examine the temporal phase relationship between rainfall, and to validate the indirect effect, we carried out temporal phase relationship between rainfall and AOD. The correlation between daily rainfall, daily anomalies of 20 to 100 days bandpass filtered of AOD and rainfall, where AOD leads rainfall by 3 days. The figure A shows the anomalies of filtered anomaly, D is the unfiltered anomaly, and C shows the spatially average correlation. Our green line shows the overall India, red shows CTC region, and for the box region indicated in the figure A and B shows in the blue. So we can observe that when AOD leads, rainfall by 3 days, there is a significant negative correlation. Coming to summary and conclusion, the active break composite analysis of rainfall, aerosols, cloud properties, and circulation field reveals significant buildup of dust aerosol over Indian region, which are transported from Africa, West Asia, and Thar Desert by large-scale circulation associated with the break. Over most part of India, the cloud effective radius is abnormally low during the break. This indicates the possibility of the indirect effect of increased aerosol under limited moisture content scenario on clouds during breaks. where increased aerosols inhibit cloud growth and accordingly suppress precipitation. And as the duration of the break spell increases, the AOD anomalies decreases systematically. In contrast, there is no clear relationship between AOD and rainfall anomalies during the active cycle. The composite break spell, the short flex is less at the top of the atmosphere, which suggests dust aerosol interact with the short wave flex to some extent, which implies semi-direct effect. In addition to indirect effects, the dust-induced semi-direct may also be effective during long breaks. The local grid point correlation between daily anomalies, the 20 to 100 day dampness filter anomalies, the AOD and rainfall during monsoon shows significant negative correlation when AOD leads rainfall by more than 3 days. This could be mainly due to the indirect impact and to a smaller extent due to the semi-direct effect of absorbing aerosol in reducing rainfall after desert transported dust aerosol build-up during the break phase. However, the magnitude of the correlation coefficient is minus 0.25, which shows that the impact of aerosol on rainfall is not very intense on intra-seasonal time scale, and aerosol impact is not the primary dominant factor responsible for the break season. Dust aerosols are not only responsible for the indirect and semi-direct effect on the break condition, but also for the increased dynamical or circulation features, and as a result can reinforce the break condition and thus extend the break speed. The incorporation of dust-induced feedback in the model is necessary to improve the intra-seasonal variability of simulation and Indian summer monsoon prediction, since breaks are the intrinsic features of ISO. Thank you all.
We know if Arya is available for questions. Is she? Arya, are you on? No? Okay. Well, if we can't do questions at this time, I guess just contact the speaker with any questions. And that's the end of the session. Thank you all.